Good morning, everyone. I am Pravin Bhattarai, currently working as a postdoctoral research assistant at Phutung Research Institute, Kathmandu, Nepal. And these are our team members, Sanket Bora, Rijan Merzen, Ian Crow, and Asim Daval. On behalf of our whole research team, I am now going to share our recent work on the design of an MMI-based spectrometer. Before we begin, I would like to share this beautiful picture that represents Nepal, the country where I come from. I would also like to briefly tell you about Phutung Research Institute. We are a small non-governmental, non-profit research lab in Kathmandu, Nepal. We primarily work in the field of optics and photonics. Spectrometers are widely used devices in chemical and biological sensing, materials analysis, and light source characterization. Different approaches have been proposed to implement high-resolution on-chip spectrometers in an integrated optical platform, such as arrayed waveguide gratings. However, the spectral resolution of this spectrometer scales with the optical path length, which requires relatively larger footprints, resulting in bulkiness and lesser compatibility for photonic integration. This limitation has led to the development of a number of alternative spectrometer designs. Example, dispersion engineering in photonic crystals. Although limitations related to backscattering and fabrication inaccuracies exist, the advantage of choosing photonic crystals as a platform for the spectrometer are their strong dispersive properties that can result in a high spectral resolution, compactness, and their compatibility with an integrated optical platform. An exemplary module of a spectrometer based on multiple light scattering in a silicon-on-chip featuring a random structure was earlier presented by Redding et al. The basic working approach is similar to the previously described other fiber-based spectrometer designs. First, light propagating through a random disordered system generates unknown unique speckle patterns, like shown in figure here, that are wavelength dependent. Second, the unknown speckles are measured and stored in a transmission matrix as shown in figure B. Such calibrated T matrix describes the wavelength dependent spectral to spatial mapping of the spectrometer as shown here. At last, any arbitrary unknown input signals are successfully reconstructed from its speckle pattern as shown in figure C. In this presentation, we demonstrate a new design for on-chip spectrometers that would suit for a wide range of lab-on-chip spectroscopy applications. The proposed spectrometer is enabled by dispersion of random holes in a 1/16 multimode interference splitter as shown in figure A, and reconstruction of the input spectrum based on a widely accepted pre-existing algorithm. The dimensions of our prototype are designed and optimized using FDDT and VAR FDDT solver, thanks to the numerical solutions. In addition, we have also optimized other parameters except MMI dimensions, such as transmission percentage calculated as the total sum of intensity collected at all the output waveguides, holes number, width of the hole filling in MMI, position with respect to the input source and output waveguides. The final optimized design parameters are listed in the table here. A sample of the simulation view of our MMI splitter, both in numerical and GDS layout in XY plane, is also shown here. A brief insight to the fundamentals of the reconstruction algorithm followed in our work is shown in this slide. The algorithm is similar to previous designs with slight modifications. First, we run an FDTT simulation using a known mode source centered at 1310 nanometer as an input. However, the source bandwidth varies with respect to the type of the input probes we shall reconstruct. For example, narrowband, broadband, or an arbitrary input probes having varying intensities at a range of wavelengths. The monitor is set up and placed at input and each output waveguides. The FDTT simulation allows to select the desired number of wavelength points where intensities are recorded and written at each specified wavelength points. In our case, the number of wavelength points are said to be 500 in a range of 1300 to 1320 nanometer of wavelength. As recorded intensities are used to calibrate a T matrix as given by the mathematical equation in 1, where I represents the intensity in the output waveguides. Similarly, S represents the source intensity and T represents the calibrated transmission matrix as a function of wavelengths. For instance, for 500 wavelength points at 16 output waveguides, the matrix dimensions now remains 16 into 500 for M and N respectively. Notably, the mismatch of the dimensions during the reconstruction in input and output waveguides are also corrected by appending zeros. After calibration of the T matrix, we need to find the inverse, which is first accomplished by implementing SBD decomposition as shown in equation 2 and further performing pseudo-inverse in Python. Finally, an arbitrary probe spectrum, yes, corrupted by noise at various signal-to-noise ratios, such as SNR equals to 100 or SNR equals to 1000, could be reconstructed by measuring the intensity of light reaching the output waveguides I and multiplying it by the inverse of the transmission matrix as shown in equation 4. In the next few slides, we'll share our results obtained after the reconstruction process. Here, we first compared the reconstruction of two narrow Gaussian input probes having full width half maxima of 0.24 nanometer and 0.04 nanometer at SNR equals to 100, as shown in the figure 1. The proposed algorithm successfully reconstructed these probes, although with noticeable differences in the reconstruction process measured as a root mean squared error RMSE. Apparently, the RMSE value was higher at SNR equals to 100 as compared to SNR equals to 1000 for every probe having full width half maxima from 0.04 nanometer to 0.24 nanometer. However, the optimal RMSE value was observed around 0.10 nanometer, even though we expected it to decrease monotonously with the increase in full width half maxima. To our understanding, a fixed window introduces truncation errors that increase monotonously as the width of the Gaussian probe increases. Next, we customly created an arbitrary probe having different amplitudes at a wavelength range of 1300 nanometer to 1320 nanometer. The figure 1 shows decent reconstruction of the given input probe at SNR equals to 100. However, it can also be noticed that few peaks that are lying closest to each other are unable to be resolved, which might possibly refer to the resolution limitation of our device. The study of noise effect in the reconstruction of such arbitrary probes in figure 2 showed that the RMSE value substantially improved at SNR equals to 100. We next tested reconstruction of a broadband probe ranging from 1290 nanometer to 1330 nanometer, expanding the range of wavelength from our previous standards in order to ensure maximum broadband range that could be possibly achieved. Figure 1 depicts a well-reconstructed probe of full width half maxima equals to 4 nanometer as compared to the 70 nanometer probe, reflecting slightly poor reconstruction. Apparently, it agrees to the previous finding that the increase in the bandwidth leads to compromised interference patterns, ultimately resulting in the poor reconstruction. Nevertheless, in terms of additive noise, there were negligible differences among the broadband probes starting from 4 nanometer to 17 nanometer, indicating that the reconstruction is quite robust at both SNR equals to 100 and 1000. To conclude, our findings demonstrate that dispersion engineer random holes based MMI splitter opens a new avenue for the design of spectrometers having good resolution, that is 0.04 nanometer approximately, as well as reasonable transmission of 67% and a very small footprint. Thank you all for listening. On behalf of the whole team, I would like to thank our funding agencies, all the partner institutions, and collaborators for their invaluable support. I would also like to extend thanks to NCS Numerical and Lucida Photonics for the simulation and design softwares. Before signing out, I would be happy to answer any relevant queries from the audiences. Thank you.